The International Space Station provides a place to do science research. There are experiments operating inside the laboratories in the station modules and others at work on the exterior of the station. One of those technologies demonstrations located on the port side of the station truss pointed down at Earth is a thing called OPALS, the Optical Payload for Lasercomm Science, which has completed its first optical downlink test in June. Recently, Brandi Dean spoke with the OPALS mission manager, Matt Abrahamson, at the Jet Propulsion Laboratory in Pasadena, California, to find out how the testing has been going this summer.
Well, why don't we start off by having you explain some of the advantage of optical communications over radio?
So optical communications is a major technology for NASA because it has the potential to provide 10 to 100 times faster data rates as compared to existing radio wave transmissions. So really, it's like an upgrade from dial-up to DSL. Radio waves are typically transmissions that are very long wavelength and that diverge quickly over time. Optical communications, on the other hand, use a focused laser beam, and they have much shorter wavelength, so they can just pack more bits of information into the same transmission in the same amount of time. So we're creating a bigger pipeline for these space data transmissions.
And you're testing that with the OPALS experiment?
Absolutely. We've had currently 18 successful transmissions from space to ground from the ISS OPALS payload to our ground station here in California. And we're demonstrating this link and validating this optical link and this new technology for NASA.
And I guess the first downlink test was in June. It sounds like everything went well, but what's the next step?
So our first downlink was actually on the evening of June 5th, and everything went just to plan. It was great. We acquired the OPALS signal once the space station was about 25 degrees above the local horizon here in California, and we maintained that signal for the total expected duration of 148 seconds. And as we were maintaining that optical link, we were transmitting a high-definition video, and it was a special communications-themed video with a message, "Hello World," and that was really an homage to the first output of any standard computer program. Each copy of this video took about 3.5 seconds to transmit over the optical link that would typically take about 15 minutes over radio. And, there's a lot of excitement here in the Mission Control Room at JPL and also at the Payload Ops Center over at Marshall Space Flight Center when we got that first transmission. It was also a unique pass because the ISS was sunlit in the sky above California for that pass, which means even though it's dark here on the ground, the ISS is lit up in the sky. So following the transmission, we actually all gathered outside and we watched the remainder of the ISS pass over Los Angeles, which is really neat.
I bet that was a great experience.
It was. And then once it was all over with, we headed back inside and we decoded the video on the ground and gathered in the auditorium to watch this Hello World video that was transmitted down to the ground. I
guess you've continued testing since then, right?
Absolutely. So that was on June 5th, and so we've gone about 3 more months now. And since our first success, we're trying to validate this optical link and try to stretch the limits of this optical link. OPALS is all about learning more information about this optical link so we can feed it forward to the next optical comm project. Our first attempt was to acquire the transmission closer to the horizon, so typically we're acquiring at 25 degrees above the local horizon. We lowered that down to about 15 degrees and found that we could get fairly reliable transmissions down there. And so not only did that increase our maximum transmission from about 900 kilometers range to 1,200 kilometers range, it also added about 1 minute of transmission time to our pass. We've also had night and day transmissions, and at different times of the day, we found very interesting things happening. Our night transmissions are extremely reliable and repeatable, but the day transmissions, while being successful, they're a little more challenging. It's a little more dependent on the sun geometry. So, for instance, we've noticed that sometimes some of the sunlight will wash out our beacon signal. So our tracking is a little bit more degraded with the optical link. And even at times, we've noticed that our system will briefly lock on to bright glints off of waterways on the ground or roadways, but then return to our beacon once that bright spot has dissipated. So we've seen a few instances of our ability to reacquire the link, even after being interrupted by some sort of disturbance on the ground. And then lastly, we've been experimenting with pointing sensitivity tests. And so we take our downlink laser and we kind of scan it over our receiver on the ground. And what we're trying to do is measure the power drop-off at the edges of the beam that's coming down to the ground. And we're looking for a sweet spot of where the maximum laser power can be received on the ground. And so based on our initial assessments, we think that we can probably, if we move to this sweet spot, increase the power on the ground by as much as 20%. So all in all, we're just trying to test out this link and see how we can make it more robust and better for the future.
Well, when you talk about the link, what info do you actually downlink?
On the link, we're typically downlinking high-definition video. So as I mentioned in the first pass, we downlinked the Hello World video. But there's a few different types of media we can send over the link. So more recently, we've downlinked a text file, and that was actually the Alice in Wonderland book, a favorite children's book of many people. We've also downlinked what's called a pseudo-random bit pattern. And so when we downlink the pseudo-random bit pattern, that allows us to measure the bit errors as they come down in real time. And then even more recently, we sent down one of our engineering logs over the optical link. And this was a big deal because it was our first downlink of space-generated data. Previously, we've only been downlinking data that was preloaded on the OPALS payload. This engineering data accumulates as we do a pass on the OPALS payload. And typically, with our nominal method for getting it down to the ground, it takes up to 3 hours to downlink it. But we thought, hey, here's a good chance to put it over the optical link. And we were able to downlink it in about 20 seconds over the optical link. So this was a major success for us.
It sounds like it. Well, I understand you've also tried some collaboration with our international partners as well.
Absolutely. And this has been a lot of fun working with our foreign partners. We've been collaborating with the German Space Agency, DLR, and they have an optical ground station at Oberpfaffenhofen, and that's near Munich, Germany. And also the European Space Agency, ESA, who has an optical ground station in the Canary Islands. And so we've been working with them to get them to be able to optically track the space station. They've both been able to successfully do that, and then prepare them for receiving the OPALS transmissions. One thing we found with them is that weather interruptions tend to be a major issue. It turns out the weather in Germany and the Canary Islands is not quite as ideal as Southern California, but we're working around that. And to date, we've had a small handful of partial transmissions, anywhere from 10 to 50 seconds in duration, that have either been occulted by geometry or occulted by clouds as we've attempted to downlink. But we're still working with them, and hopefully we'll get fully successful downlinks soon enough.
Well, now that you've accomplished all of this, what is the next step for the project? What do you want to do next?
Well, we're just ending our prime mission now, and so we do have an experiment that will be starting up in the fall for extended operations, and that is to experiment with an adaptive optics system supplied by Boeing. And the idea is to increase the efficiency of the optical link. It basically uses these adaptive optics to try to get more power out of the receiver on the ground when we transmit. And so we'll have a stronger, more robust link that possibly we can transmit from longer ranges and lower elevations relative to the horizon. So like I said, this will happen in the fall and winter of this year. We also have a proposal out to possibly characterize the ISS platform vibration environment using our laser and camera on board OPALS. And I think we'll also have some more foreign partner collaborations ahead. We're looking at working with JAXA as well, the Japanese, and I think there's a lot more work to do in that area. So I think this is just the first step for the prime mission, and that there's a lot ahead here with OPALS.